You're right, yeah. So this is last of 3 talks on this kind of gravity-like connections. And hopefully, at the end, this will contain a punchline. Punchline is that a particular 4D gravity theory admits very nice geometric interpretation from the point of view of 7D, but this gravity theory is not GR, and so this will leave us with a puzzle, why GR, so to say. But I'll start by reminding you what GL described in the morning very quickly, and mainly to establish notations. So I will start in 4 dimensions. I have an SL3 connection on a 4-dimensional manifold. This is the curvature 2 form. And then the idea is to construct an action principle, diffeomorphism invariant action principle for connections without having any metric. And the way you do it is you take Fi which Fj, you pick a reference volume form, we call it V, and you use the volume form to define the matrix X ij. So basically X is just F which F divided by V. Of course, V is defined only modular multiplication by a function, and so is X. And then we construct an action as a nonlinear function of this matrix X. So I take a function which will map 3 by 3 matrices to reals, and this function will satisfy 2 properties. One is homogeneity degree 1, and second property is gauge invariant in the sense that well, I have a natural action of orthogonal group of 3 by 3 matrices, Lx over transposed, and I require the function to remain unchanged. And of course, there are many such functions. Well, I will describe how many after I write the action. So I need a function like this because then I can define the action to be integral of f of x times v. And this is an invariant definition because if I rescale v function, because of homogeneity 1 property also rescales, and so this is an invariantly defined 4 form which I can integrate. And how many functions like this are there? Because I can always write x, I can diagonalize it by orthogonal transformation. I can write it as diagonal lambda 1, lambda 2, lambda 3 with transposed. My function of x is really, say, lambda 3, function of lambda 1, lambda 3, lambda 2, lambda 3, 1. So basically, there are as many such functions as functions of 2 variables. Of course, they must be special. There must be some symmetry property that comes from the fact that one can exchange the eigenvalues. But there are many such functions. And I'll give particularly interesting, relevant examples of such functions later. So right now, this is a diffeomorphism invariant theory of SL3 connections. Let's look at Euler-Lagrange equations. Derivation of S is integral to df by dx times the variation of x, which is the variant derivative of the variation of the connection, which curvature. And then you integrate by parts. So you see that Euler-Lagrange equations for this theory is a statement that the variant derivative of df by dx by j f j is equal to 0.
Sorry, that was a slightly different way from the way that Joel said it, though. So he just said you take an invariant, set it equal to constant. Is that f actually just any combination of all the invariants? So sorry, the f is a functional combination of the invariants.
What Joel described is a different functional. He had a functional that depends on a 3 by 3 symmetric matrix and the connection. And this functional was integral, basically, Pij, well, maybe minus 1, Fi, which Fj. And then one adds here a Lagrange multiplier imposing some condition on P. So for example, trace P is equal to 1. And then you can integrate out P from this by solving its algebraic equation. And you'll arrive to pure connection formulation of this sort, where this F is basically a Legendre transform of whatever condition imposing function you have here. So this is how you get from one formulation to another. So important thing about these theories, it's important to realize that this is a class of theories, right? Very large class of theories. The equations that you get for any f are second order PDEs on A. And then an exercise in Hamiltonian analysis. So you do 3 + 1 split, you analyze what constraints are, tells you that there are 2 degrees of freedom. This is a completely non-perturbative statement, in the sense that, well, you just see what the constraints are, what the algebra of constraints are. These are 2 degrees of freedom, 2 propagating degrees of freedom here. And to understand what these degrees of freedom are, you can then expand around given background. So for example, you take some constant curvature background, expand, and you see that these 2 degrees of freedom are spin 2. There are 2 polarizations of the graviton. 2 gravitons, 2, well, plus minus of gravitons. So all these are gravity theories. In the sense that, of course, this is all non-Lorentzian. So these are gravitons in the sense of, well, gravitons in Riemannian signature GR.
The simplest example of this is presuming that f is just linear in x.
In that case, any connection will satisfy the Euler Lagrange equation.
But that seems to be rather degenerate case, right?
Yeah, this is so. Yeah, I'm assuming that f is generic.
I see. But
F
the
is
claim
not
is
the
that
trace.
for a generic f of this type, genuinely do get propagated degrees
Yeah.
of freedom.
Yeah.
Like this.
This is the statement. Yeah. For generic f, there are 2 propagated degrees of freedom. For the special case, of course, there aren't 8 degrees of freedom. Every connection is gauge equivalent to any other. Any connection satisfies field equation. But this is a completely degenerate case. So.
And so the Einstein case was when f is...
Yeah, then let's look at some examples. Well, actually, before I look at the examples, I need to describe in which sense these theories are gravity theories. So I need to describe what the metric is. Metric is constructed in 2 steps. One step is constructing conformal class. And this is easy. Well, Gerald had a formula on this, so it will be pairing of 2 vector fields. And it's a conformal class. This is why I put a proportional to. It will work with epsilon ijk. You insert first vector field into fi. You insert second vector field in fj, and you wedge fk. And well, we need to divide by some volume mu, because this is a 4-4. But of course, as a conformal definition of conformal class, this is good enough. So this is conformal class. And we also need volume form to fix the definition of the metric. And the volume form you take to be f of x mu, right? It's the volume form which defines the action of the theory. With this choice, the action of the theory is just the total volume of the space. This is very natural, right? Take that metric of whose the action is the volume.
This is plus or minus the right answer, depending on whether the connection is positive.
Right, yeah. Because, well, there is a sign of the connection. I'll explain that sign later. Yeah, of course, the connection has a sign, and this metric may come out to be all negative signature, and this is why you may need to put a minus sign here. So this is metric, and then there are 2 examples, particularly interesting. First example is GR. You can describe GR in this way. And for GR, FGR that you take is trace square root of x squared. And the reason why this is GR is the fact that for this function, you have the property that df by dx f, which df by dx f is proportional to identity. The two forms that appear there, the wedge product is proportional to the SO3 invariant metric. And what this implies, it implies that A is a Levi-Civita connection on lambda plus. And then from here, metric is Einstein. This is what Joel explained in the morning. The second example, I'll call it that X theory, because you take F to be the determinant of X on 3. Oops. That X1, 3, and well, you need to take this particular root for it to be homogeneity degree 1. Then Euler Lagrange equation what you get is that X 1, 3, 1 X F is equal to 0. I forgot to say that in this case, df by dx is proportional to 1 over square root of x. And this is the reason that gives you the identity matrix there. Here you instead get 1 over x in field equations. This theory is interesting because, in a certain sense, it's simpler than GR. If you look at solving the rising differential equations, then you get things work out simpler than in the case of GR. So we'll call it mathematically nice theory, and again, it's simpler than GR in some sense, in the sense that things work out simpler. But that I'm not going to explain. And I should also explain, Joel explained the fact why this particular choice of the function is mathematically preferred. Let me say this as well. It's related to the fact that, well, this choice of function f is the canonical in the definition of the matrix. So, motivation for that x with 3 comes from the fact that, remember, I defined my metric in 2 stages. I first defined conformal class and then volume form. You can combine this definition, and actually this is what leads to this theory. So, I just define the metric to be that formula, so IJK like psi fi by eta of j which fk divided by the volume form for this metric. We should call it VF. So of course, well, the way this definition works is so that square root of the determinant of this metric is the volume form that you're using there. Do I need, well, let me note, one can say more on this, one can determine scaling, the way this function, the way this volume form depends on f, but I don't think I need this now.
But the connection has torsion in this case.
Yes, the metrics arising in the metrics solving. If the connection solves its second order PD, in this case, the metrics arising are not Einstein. Yeah. Connection is not a Vichy.
So the curvature is, in some sense, has the right.
Curvature will be self-dual by definition, by construction.
Yeah.
But it's curvature of the wrong connection.
But the torsion is somehow.
Yeah.
So,
An interesting question that we don't know an answer to is geometric interpretation of rising metrics. Can one
the
characterize?
torsion could maybe be interpreted as another spin 2 field that's propagating or something.
Definitely not, because we know that these theories just propagate 2 degrees of freedom.
Actually.
So this is not, it's not gravity plus additional matter fields.
Right.
This is wrong interpretation. it's somehow gravity, but deformed in a strange way. The way in which the number of degrees of freedom is unchanged, but at the same time you don't have Einstein metrics anymore. And I should also emphasize even the fact that here I'm describing to you gravity theories with two propagating degrees of freedom is very strange. It goes against one's intuition about GR uniqueness. This needs to be emphasized. Here I'm explaining concrete set infinite parameter family counterexamples to GR uniqueness. Of course, modulo the fact that I'm doing things in Riemannian signature and in terms of connections. So it's very, very difficult to see what these theories are in metric terms. One can characterize them in some way by, for example, computing gravity and scattering amplitudes, and then you see that they start with GR plus Riemann cube. But you also expect that this is an infinite series in terms of high order curvatures. High order curvature means series that doesn't stop. So this is the right intuition to have about them.
So I missed an issue. You say the curvature is self-dual.
By construction, you declare, the way this formula works.
The curvature of the connection, not the curvature of G.
The curvature of the connection, yes. The way this construction works is that this matrix makes this triple curvature self-dual. It's designed to do that. This is the way this matrix is constructed. Okay, so I think this is all I need for the 4D story, and then let me describe three forms in 7 dimensions, some simple geometry, simple geometric parts of that. Apologize to experts in the audience. This is very simple. So my 7D manifold in middle in P. Later on, I will take it to be the principal bundle over 4D base. So it's 7D. Then dimension number 3P is 7, 6, 5, 3, 5, 5. So it's 35. And then there is a notion of stable forms, which lie in open GL7. So GL7 orbit. There are two possible orbits over reals. Orbit of positive type is GL7 node G2 compact form. Dimensions work out correctly because this is 41 minus 40, so it's the same dimension of lambda 3p. And the form of this type can be written as E5, E6, E7 minus E5, sigma 1 minus E6, E2 minus E7. 3, where sigma 1 is equal to E1, which E2 plus E3, E4, etc. So this is the basis. So these are self-dual sigma I basis number plus. So here the statement is a form that lies in this orbit admits canonical form of this type. You can always write the form here like this for proper choice of the E's of one forms, E1, E7.
So, sorry, this is probably a stupid question. So these sigmas are a basis of self-dual two forms of some four manifold.
Yes.
So what is the relation of the form? It's the base for some
Later
rank
on it will
three.
be interpreted as a base. Yeah.
This is just linear algebra.
Yeah.
Right, okay.
This is just linear algebra. And I could also use, usually in the literature it's anti-self-dual forms that I used here and then the plus, but this convention is like a medium for later. And then negative type is GL7. It's again G2 but non-compactorial form. Same count of dimensions, but the canonical expression for it is E5, E6, E7, now plus E5, E1, E2, E7, E3. It's just a change of sign there. Okay, the most important fact about three forms in 7 dimensions is that they define a metric. Well, generic three forms in 7 dimensions, these stable guys. You can get the metric just by, if you write the form in this canonical form, you can just read off the metric. This is the frame for the metric. So, omegas that are stable, they give the metric. And with G is just the sum, well, because we some signs, so we should write for the positive case. For the positive case, the metric that you get is Riemannian, all plus signature, and it will be just EI, sum over I, 1 to 7, this is positive. So it's all plus. For negative type, you get a speed signature matrix, 3, 4. You get in the sense that there is some other definition of the metric. So this is the answer for some computation. And I should tell you the other definition of the metric. The other definition of the metric is actually a variant of this formula. But I will erase it by the formula in terms of three forms. So metric is psi eta. You define it again by choosing auxiliary top form, auxiliary volume form, and then you get x and omega, eta, omega. This is 2, 2, 3, so well, this is a top form, and then you divide by the volume. And the most canonical choice of the metric, the omega, is to put the volume form for that metric there. So this not only defines the conformal class, it defines the metric completely. And then it's a computation that for a form of this type, of positive type, you get a Riemannian signature metric. For a form of negative type, you get speed signature metric by this computation. I think at this stage I want to do simple computation and see how my volume form scales if I rescale omega. That I will need for later. So let me compute the determinant, which is metric g omega. And I'll write it very schematically. It will be determinant of something cubic in omega. So determinant omega divided by because this is the square root of determinant g omega, 7th power, right? Because I'm in 7 dimensions, so this is what I will get. And this tells me that, so this is 7 halves, overall this is 9 halves, so I get determinant g omega, square root of, it scales as omega of 7/3. Because this determinant here behaves as omega to the 21st power, so this is why I'm getting 7/3. right. Well, yeah, this is the correct scaling. The scale is omega 7 hertz. And then, so volume functional. Volume functional as a omega is integral v omega. I also need expression for the dual form. Now that I have a three form and a metric, that is three form defines, I can take the Hodge dual. And if my three form is written in the canonical form, I can write the dual form explicitly. It is sigma I plus, well, there is a sum over I here, plus 1 over 2, no, I just write it as u5 e6 sigma 1 plus 2 more terms. And the sign here is plus for the positive type case. So this is for the positive type. And the last part that I need is what the variation.
I think you might mean sigma 3, there are 5, 6 sigma
5, 6, sigma 3. Yeah, you're right. Yeah. Last fact that I need is what variational principle for this volume functional gives me. To derive that, I use it that I can write this volume as a multiple, appropriate multiple of the dual form and the form itself. And then the variation of S is again appropriate multiple of omega Hodge star, which variation of omega. All these multiples are determined by homogeneity. And in particular, this tells us that if we vary omega in fixed cohomology class, so if d omega is equal to 0 and delta omega is some d of t form, then the critical points are solutions of this equation. The dual full form is closed. And then there is a fundamental theorem that d omega is equal to 0 and d omega star is equal to 0. These together, this means that the metric that omega defines is G2 homonymy metric. Okay, this is all I need about the 7D, and then I describe the 7D lift of the 4D story. What I want to do is just to copy the three-dimensional construction that I explained yesterday. So I'll take my utility principle. and I will take omega just to be the Chern-Simons free form in the double space. Of course, I immediately notice that the omega, which is equal to trace f which f is equal to Hunterian number for this bundle, in general it doesn't have to be 0. And actually, we want to consider the bundles for which this is not equal to 0. So for the forms, three forms that I'm taking, I'm not going to produce G2 structures. I'm not producing G2 over manifolds. But you will see that, well, still this. So maybe I should say that, well, the motivation for this construction is that if you take S4 as your manifold and follow this construction, then the P that you get is S7. In the sense that, well, we get a particular principal bundle of four-dimensional waves, and the bundle in this case is going to be S7. So the construction is interesting, at least in this case, and this is why I'm going to generalize it for more complicated connections. Okay, and well, then the rest is a computation. I have a free form. I want to understand what my volume functional in 7 dimensions gives me. So I want to compute S times A, and I want to see that this is some S of A. I want to find real quantities, and I also want to understand what the condition V omega star is equal to 0 gives me. It's not clear that this condition will be a critical point, because we don't have the closure of omega here, but it will be. So this will follow varying. If I vary the connection now, if I vary free form by varying the connection, this will be still a critical point of my volume functional. And the other computation I would like to do is what is the metric that this omega defines. And we will see that, what one gets is this that x to power 1/3 theory, and all the geometrical notions that were introduced in 4 dimensions appear here very naturally. They're the 7D geometrical notions. This computation is instructive, so let me do it. And after I do this computation, there is a variant of this construction that works not with principal bundles, but with R3 bundles. And in that case, you can get G2 structures. That I'm going to just state like that. I think this construction is more geometrically useful. This is why I'm explaining it. So let me take, as I said, omega is Chern-Simons. Well, let me do 2 here. Let's do trace ABA minus plus 2/3 AQ. I write it as 2 trace H F minus 1/3 AQ. Then here connections are 2x2 anti-initial matrices, and I go into SL3 matrices. This becomes 1/6 epsilon IJK and IJK minus and then to do all the computations, what I need is just to write this guy in canonical form. To do that, I write my Fi as square root of X matrix Ij sigma j. So I'm using the fact here that I can always declare the curvatures to be self-dual with respect to some metric, and sigma I is an orthonormal basis in the space of self-dual 2 forms for that metric, and so I can always write the decomposition like this. This way of parameterizing the curvature would allow me to find the canonical basis. Then, well, if I should do the computation, I should just state the result. Well, I mean, Okay, let me just take the result for omega star. Omega star, computed this way, is fi determinant x 1/3 omega x mg plus ijk ij. And again, this is that x 3 omega x f. Okay. So the full form is constructed either from the connection itself, or from F, or from this block. This is the same block that appears in field equations, so that x theory. And then you can see what the condition that this form is closed implies.
So that's the field equation saying from deforming omega by closed two form.
Again, the logic of what I'm doing here, I took a chance elements of A, this is my 3 form, and then I just computed the dual form by, well, the idea of this computation, I'm looking for the canonical basis.
Oh, so this is a dual.
This is a dual
So that
form.
tree form determines a G2 structure, and that's just a dual two.
Yeah,
form.
this 3 form determines symmetric, and this is just a dual form. And that,
Okay.
the way you compute it, you put this guy in the canonical form, you read off what the forms are, and then you immediately write the dual form. Even though the square root of x matrix appears during the computation, at the end of the computation, it all combines into 1 over x. And the various factors of that x appearing. So this is the dual form. And it's, even from here, it's already sort of clear that this form is closed. Well, clear that if dA x on 3 over x f equals to 0, then d star omega is 0. This is easily checked. Well, if you act with a d, you can act with Carrier derivative instead. This action on this is 0 because this is Bianchi identity. Acting on the whole block is your field equation. Then here, acting on this block is a field equation, and then acting on A gives another factor of curvature, but with the epsilon. And then because there are 2 epsilons, actually, I think no. Acting here on A just gives you the curvature, but there is epsilon curvature. The curvature is something symmetric hitting the epsilon. And this is why it's 0. So this form is closed if the field equation of that x 1, 3 theory is satisfied. Okay. Then another simple computation is to compute V, the volume form. That is computed just by taking the wedge product of omega and its dual. And it's clear that what one gets here is, well, basically it's the A cube times this block. In this block, f wedge f, you get a trace of it. So this volume is just proportional to epsilon ijk ijk times that x 1, 3 times the volume form of the metric. And so this means that our volume functional on this 3 form, this factor integrated over the factor just gives the volume of 3's here, and this factor is integral that x 1, 3. This is another way of seeing that 7-dimensional theory gives rise to 4D that X theory because the actions are multiples of each other. Obviously, this is consistent with the fact that Euler-Lagrange equation, we obtained the Euler-Lagrange equation reduced to the Euler-Lagrange equation of this theory. And then the last computation I want to explain is
Sure, can I ask a question? So if you think of S7 as a half vibration on CP3,
Yeah.
does that give you some twistorial description of your model?
why on CP3.
Well, I mean, just twistor spaces. So CP3.
Well, all this is related to the usual twistorial description. Twistor bundle is S2 bundle, and you can think about those. Well, S2 bundle is a projectivized C2 bundle. And actually, yeah, you can think about S7 as C2 inside C2 bundle over R4 over the four-dimensional base. So in that sense, there is a relation that the almost complex structure that one uses, or almost complex structure that becomes integrable in twistor theory on instant on spaces, is not the one that arises here naturally. The one that arises here naturally is a different one that is not integrable. This construction is similar in spirit in the sense that one encodes information about the geometry of four-dimensional base into the total space of some bundle. So, finally, I want to describe the metric. The metric that this omega defines. And this is the same computation. You read off what the frame is, and then you write the metric. This metric is x minus 1, 3 x energy. Well, I write it as a x a. This kind of product here. These are one forms, and so this is. Using the expression for the metric in terms of the frame field, and then plus GF. This is the metric that arises in the fiber. This is the fiber metric. This is the metric that arises on the base. It turns out that the metric on the base is just the. This is the metric we already encountered. This is the natural metric on M. From connections. With the volume for ZX 1, 3, C. This is the canonical one. This is the mathematically natural one. And this is a metric in the fiber. So, knowing this, you can also state the field equation as dA inverse fiber metric acting on F is equal to 0. So it's the same gadget, but the inverse of it that appears in the field equations. Okay. And I should also say that remember, in the story that Joel explained, there was a sign of a connection, and there was a notion of definite connection. So, if you start with a connection and take this tree form, then the notion of definiteness is just the notion of stability of this form. The connection is definite if and only if this tree form is stable. And the notion of sign is just captured by which orbit your free form lies in. There are two real orbits, positive and negative type, so the sign of the connection is just which orbit this Chern-Simons free form lies in. So let me summarize this construction.
So does this in the self-dual case, and this extends the Bryan-Salomon construction, does it? Is that,
No, it does not. So I will, once I summarize this, I will give you the
Sorry,
construction. The Bryan-Salomon construction works with R3 bundles.
Oh,
This is the
okay.
principal bundle.
right.
This omega is not closed. Remember?
Yeah, the omega is not
D
closed.
Oh, right.
It's never closed.
Of course, right. So it's not a G2.
It's like a
It's
G2
never going
construction.
to give you G2.
Oh, okay, sorry.
It generalizes the S7 construction. It generalizes the Hopf vibration,
Mm-hmm.
S3 over S4. Okay, so solutions of natural gravity theory. That's an A integral of x 1, 3 can be limited to 7b in natural range. Take omega is equal to train sinus of A. You got the omega is equal to Pythagorean. D star omega is equal to 0. Metric on the base of M is just the restriction of the natural, of the canonical metric defined by omega to the base, in this case. Then action functionals agree, and so chain sinus of omega is just, well, is a multiple. If it's integral of x 1, 3 VS3. And in particular, this equation is Euler-Lagrange equation arising from this action. And so, as I said, this generalizes S7 as a whole vibration over S4 construction. There is another layer of this game where you can get G2 structures. You can take instead little space of R3 bundle. And then you can write less canonically looking form, but it's possible. Omega is some function. So my yi be coordinates in R3 in the fibers, and then I write 106 alpha cube epsilon ijk dy ai dA dA plus 2 sigma alpha beta squared dA yi wedge fi. And so for appropriate functions alpha beta functions of R, where R is equivalent to the sum of y squared. This form is closed and composed. And these appropriate choices are the same as in Bryan-Salomon construction. And this is generalization of Bryan-Salomon, but it works provided in the case that x 1 over f is equal to 0. So again, critical points of the same 4D theory can be lifted, but now to G2 structures, G2 holonomy metrics.
These G2 holonomy metrics, they're not, they have the same incompleteness phenomenon.
Exactly the same, yeah, the functions are the same. So they are complete only, I think, in the positive case, when connection is positive, I think. Then the functions arising will not have any nasty singularities.
And up in the top case, when you're using the Chern-Simons form, you said that for negative definite, I get this split signature
You will
metric.
get the split signature metric. And this is an explanation why you put sigma in front of the metric in the definition of the metric in 4D case. This is exactly that sign. Because you get 3 4 signature metrics, so in order to make the 4 positive definite, you just put a minus sign in front. Okay. So I think this is all I wanted to say, but I want to end with a question. So I don't know if I convince you, but looking at details of all this, it seems that it is this dead X theory that is mathematically very nice theory. It does exactly what you want, you don't make any strange choices in the definition, so this is a mathematically nice theory. Then the question is, why GR? Why is the real world described by general relativity? Why are we not using this theory? So there are some, of course, aspects. There are some nice aspects about GR. The fact that in GR you get the geometric meaning of the equation that we get is a statement that the connection one starts from easily reach you to connection for the metric. So this is geometrically nice. This is the only nice aspect of the GR construction. This story is much more convincing, and well, at least to me there is a puzzle here. How one can obtain GR within this scheme of things in as convincing way as this theory is obtained. Thank you.
When you were talking about your Hamiltonian analysis and you said that you got 2 propagating degrees of freedom, so spin 1 also has 2 propagating degrees of freedom in 4D. So how do you see that they're spin 2?
Right. That you need to expand around the background and see. So, well, the reason why it's spin 2 is that it's a connection, but it's SU2 connection. So one spin comes from here, another spin comes from there, and the background is what identifies you, the internal and space-time index. So it is spin 2, and well, you analyze linearized theory, and you see that what propagates is spin 2.
So that I, in the end, it turns into a Lorentz index. When you expand the rest.
Well, yes, this is one, but it's spin 1 plus spin 1 with everything else projected out. This is why it's spin 2.
Does this theory have the same weak field limit as GR?
You mean this dead X theory, or?
Or maybe this whole class? You said you thought it started mentioning it was R plus RQ.
Right, in that sense it does, yes. But of course, the general theory for this class contains a Riemann cube, which GR doesn't, so in that sense it's different. So GR is a special member of this class of theories, in the sense that it doesn't contain any Riemann cube. So interactions of gravitons are different in the generic member of this family.
So you were forced into this dead-X theory just from the way in which you wrote down omega in terms of the A's and F's.
Yes.
But you didn't have freedom to change that ansatz so that you could put some different invariances there.
There is no natural construction that I know of that would produce GR.
You could put in a matrix between the AIs and the F's.
Nothing that we
AI
tried.
sigma instead of AI.
Nothing that we tried works. There is nothing natural that we could come up with. So the puzzle is whether GR admits a lift to 7 dimensions. This is what you want, because one can say that this 7D lift of that X theory is a twistorial description of that gravity theory. Right? This is very much a twistor theory. We want to encode.
So, a comment in that direction, you can really genuinely get to twistor space in the symplectic forms that I didn't tell you about earlier. I've just realized. So you pick your favorite copy of S1 inside SU2
Yeah.
and divide P by that S1.
Yeah. Mm-hmm.
If you integrate this 3 form down that
Mm-hmm.
codimension 1
Mm-hmm.
map, you'll get a 2 form or a 6 map form,
Right.
which will be the symplectic form.
Right.
that sixth manifold is the twistor space. So,
Yes, yes.
and then this metric is S1 invariant.
Yes.
So it will descend to a metric on the sixth manifold. And I wonder what this equation d star of omega equals 0 says for that metric on the sixth manifold.
But the natural, almost complex structure that you can get from this story, you don't expect it to be integrable. So you shouldn't land on the usual twistor.
In the positive case, I would expect it to be perhaps integrable.
Well, that we can discuss later.
Can you couple these things to matter?
Not in any simple way, but what you can do, you can take larger gauge groups. Play similar games with diffeomorphism they engaged with large gauge groups. And you get gravity coupled to various source of matter. Then in this case, there is more ambiguity. You see, the new aspect of this story is that this 7D construction fixes for you the function in a canonical way. This is what was missing for a long time, because in 4D there is just ambiguity in which functions you take. There is one that gives you GR, but there is no geometric motivation for it. This is the geometric motivation for this text. If you take larger gauge groups, then you would want to play the same game with total space of the bundle, but then it's not clear what the right geometry is. So it's not clear which function to take. But presumably these games can be played. We haven't done it.
So, related question, can you supersymmetrize the theories?
One can, for example, you can take internal space, the fiber to the supermanifold. Yes, something will result by construction of this type, but again, nobody has done it. It will be gravity coupled to various ferromagnetic matter, but it remains to be seen what you do.
But the expansion in the higher derivative presumably should also contribute to something in the ultraviolet behavior of the theory.
Well, the only thing that I know of is that all these theories are as non-normalizable as GR for the same reason. The interactions are derivative interactions. Derivative. It's a very simple reason why they're non-normalizable. You typically get, for example, in this theory, the typical interaction you get a cubic level is the A cube, and of course, it is non-normalizable.
We thank Kirill again.